Hey guys, and welcome back. I have a new video for you today. Today we are going to be talking about the Sun. Now, the Sun is the largest object in the solar system in both diameter and mass, so in both size around it and how much mass of it there is, it is the largest object in our solar system. The Sun contains more than 99% of all the mass in the solar system. So, of everything in our solar system, meaning our Sun and the planets that go around it, if you took all of that mass and put it together, the Sun is still going to be 99% of that. So that is just tells you how massive our Sun is. Okay, so we're going to get into some properties of the Sun. The Sun's interior is completely gaseous due to its high temperature, meaning that it is made up entirely of gas. The Sun burns at 9,941 degrees Fahrenheit, so roughly about the same temperature as my classroom. And this is due to this extreme temperature, the gas that makes up the Sun exists in a state known as plasma. Now, we're not going to get into like what plasma is and why that whenever gas gets to this temperature it's considered plasma. That's for a higher level class than what this is. But all you need to know is that whenever gas gets to this extreme of a temperature, it becomes known as plasma. It is considered a different form of matter. Now, the forms of matter that you're going to be most familiar with are gas, liquid, and solid. You know, solid is anything that you can. This is a solid. You know, water, that's a liquid. The air we breathe is gas. But whenever gas gets to an extreme temperature, and there are some other specific characteristics, it becomes known as plasma. And now plasma can only exist out in space. You're not going to come across plasma in your daily life, so you don't have to worry about that. Okay, let's talk about the atmosphere around the Sun. The Sun's atmosphere is made up of three layers. The photosphere is the innermost layer of the Sun's atmosphere, and it is also its visible surface. It has an effective temperature of 9,980 degrees Fahrenheit and is about 250 miles thick. And that's about the distance from New Martinsville to Washington, D.C. Now, this is the atmosphere, meaning this is what's around the Sun. So, it's 250 miles thick. That's a lot of atmosphere to be around the Sun. And you have to think how big the Sun is. It's 99% of the mass in our solar system. So, and then 250 miles out in all directions around it is this photosphere. So, and once again, like I said earlier, that's the distance from New Martinsville to Washington, D.C. So, this is a massive layer of atmosphere, and this is just the first layer. There's three different layers. Outside the photosphere is what is called the chromosphere, which is approximately 1,553 miles thick and has an average temperature of 26,540 degrees. 1,553 miles is roughly the distance from New Martinsville to Jamaica. So, we're getting to see just how big the atmosphere is. Now, usually the chromosphere is visible only during a solar eclipse, but astronomers can use special filters to observe it when the Sun is not eclipsed. So, over here on the side I have a picture of whenever you can see the photosphere of the Sun. The outermost layer of the Sun's atmosphere is called the corona, and this extends 3,106,855 miles from the outside edge of the chromosphere and usually has a temperature of about 8,999,540 degrees Fahrenheit. Now, you might be thinking, Mr. Sims, those are oddly specific numbers. Well, whenever scientists are looking at this sort of thing, they don't use miles and Fahrenheit. They don't use those kind of measurements. For temperature, they use a unit called Kelvin. Now, the book and the information that I'm pulling from to make this video, put all of the temperatures in Kelvin and put all of the distances in kilometers. Whenever I was making this video, I converted those into Fahrenheit and miles because I know that's what you're going to be more familiar with. So, the outermost layer of the sun's atmosphere gets up to 8,999,540 degrees Fahrenheit. Okay, so the next thing we're going to talk about is solar wind. Gas flows outward from the corona at high speeds and forms the solar wind. As this wind of charged particles, called ions, flows outward through the entire solar system, it bathes each planet in a flood of particles. So this is constantly being emitted by the sun, and it just coats all of the planets in the solar system. These high-energy particles collide with gases in Earth's atmosphere and cause the gas to give off light called the aurora. Now, I have a picture here on the side of what the aurora is. You've probably heard it referred to as aurora borealis, or the northern lights, or a name like that. Now, this is only viewable under normal circumstances in the on the more northern part of the planet. Now, there have been very rare instances where it has been visible close to our area, but I've never seen it. Usually to see this, you're going to have to go into northern Canada, northern Alaska, close to the northern pole, to see the aurora borealis. Once again, we could get into the down on the microscopic level of the processes that are causing this, but once again, that's more upper level stuff, so I'm just wanting to give you a basic knowledge of what it is. But these are highly charged particles that are coming from the sun and hitting into our atmosphere, causing this light. So that's what the aurora borealis is. A couple other solar activities we're going to talk about. Solar flares. A solar flare is a violent eruption of particles and radiation from the surface of the sun. Now, the sun is constantly burning, and we'll get into that process here in a minute, but occasionally, like, it'll build up and it'll be a sudden burst of more particles and radiation, and that's called a solar flare. The next solar activity is called a prominence, and this is an arc of gas ejected from the chromosphere, or gas that condenses in the sun's inner corona and rains back to the surface. Prominences can reach temperatures of over 8,540 degrees Fahrenheit. Now, this picture here shows a prominence. Let me get my mouse here. See this steam? It looks like a stream of fire or lava coming off of the sun. Well, that's what's called a prominence. Now, that's just gas. It's not a solid. And it will come out, burn, and then it'll crash back into the surface of the sun. That's called a prominence. Okay, so I'm going to give you a little bit of a warning here. Now, the next information here, what powers the sun, this is going to come off as confusing. So please bear with me until we get to the end. I promise it's going to make sense once we get to the end of it and I get through the whole process. It's going to seem a little overwhelming whenever I'm first explaining it, but just stick with me. Don't give up. Hang in there. We'll get through it. Okay, what powers the sun? Fusion is the combination of lightweight atomic nuclei into heavier nuclei such as hydrogen fusing into helium. Bear with me. In the core of the sun, helium is a product of the process in which hydrogen nuclei fuse. Don't give up. Stick with me. The mass of the helium nucleus is less than the combined mass of the 4 hydrogen nuclei, which means that mass is lost during this process. Okay, let's stop there to unpack what we've talked about so far. So, the process that powers the sun is called fusion. Now, this fusion takes, and we're talking on the most microscopic level you could get to. We're talking about individual atoms, the building blocks of everything around you, including yourself, atoms. So if you take in the sun, if you take four hydrogen nuclei, and under that intense temperature and pressure of the sun, they are going to fuse together to make one helium nucleus. Now, the thing about that is whenever those 4 hydrogen atoms combine to make one helium, the helium is actually smaller than the 4 hydrogens are. Imagine if you took 4 textbooks, you stacked them one on top of the other, but then whenever you put that 4th one on there, it shrinks down into the size of a playing card. You put the 4 books, and then it shrinks down into... That's confusing. It doesn't make any sense to us. Now, if you were a person who studies physics, you would understand this process. Once again, this is not a physics class, this is just Earth and space science. So, what you need to know is that the process that powers the sun is called fusion, and it is the fusion of 4 hydrogens into one helium. And once again, whenever you take those 4 hydrogens, you put them together in this sort of situation, you make one helium, and it's smaller than the 4 hydrogens. Now, this is going to tie into a theory that was put out by Albert Einstein. Albert Einstein's special theory of relativity shows that mass and energy are equivalent, and that matter can be converted into energy and vice versa. Hang on, don't give up yet. Einstein's special theory of relativity explains that the mass lost in the fusion of hydrogen to helium is converted to energy, which powers the sun. So, let's go back, those 4 hydrogens, whenever they merge together, this process of fusion, and they form one helium, that mass that was lost gets converted into energy. And that energy is what fuels the burning, which is what fuels the sun. So, that's just going to keep on going. The fusion of hydrogen to helium is converted to energy, which powers the sun. So, what do you need to know from this portion here is that the fusion of 4 hydrogens to one helium converts into energy, and that powers the sun. Okay, so we've talked about how hot the sun is and how it's just constantly burning and putting off this energy. How does the Earth not just burn up? Well, first off, the sun is 94 million miles from the Earth. So the fact that we're that far away from it disperses some of the heat and radiation there. I mean, think it's like being at a campfire. If you're right next to the fire, you're a lot hotter than you are if you move your chair back. So that's one of the reasons. But the major reason is our atmosphere shields us from most of the sun's energy. This is why preserving our atmosphere is so important. Without it, life could not exist on the planet's surface. There was a time in Earth's history, before life, before the Earth looked anything like it looks like today, it did not have an atmosphere. And it was just getting barraged. It was just getting hit over and over with this unfiltered energy from the sun, and it was just pummeling the Earth. But over millions of years, the Earth eventually got an atmosphere, and it started to shield from the sun's rays. And that is what made life able to start on the planet. So this is why all those environmental protection things that go into protecting the atmosphere, preserving the atmosphere, are so important, because our planet could not exist. Well, the planet could exist, the planet would be fine, but we could not exist. We and all the life on the planet could not exist without the atmosphere. Okay, so the sun's spectra. This refers to the light given off by the sun. Scientists can analyze the light itself to determine what elements are burning to give off that wavelength of light. A simple example of this is when light shines through a glass prism or a crystal, it refracts the light into different colors. Now, each element, whenever it is burning, gives off a certain hue of light, a certain color of light. And scientists can analyze the light coming from the sun to tell what is burning in the sun to generate that light. You know, obviously, we've talked about how much temperature and pressure and everything that the sun has. That's why we can't just go there, obviously. There's nothing that can withstand that amount of temperature. So that's why we can't just go to the sun or get a sample of it. By analyzing the light given by the sun, observing the spectra of colors and the emission lines, scientists can deduce what the sun is composed of without going to the sun directly for a sample. Through this analysis, scientists have determined the sun is mostly hydrogen and helium. Now, there's a chart on the screen here that tells what other elements the sun is made up of, but the most of it is hydrogen, 71%, and helium, 27.1%. Now, all the other elements that are in the sun are in very small amounts. You know, over there, if you look, oxygen, which the O, that's the chemical symbol for oxygen, is only 0.97%, and all the other ones are just smaller as it goes down. Clear at the bottom of the list, we have iron. Fe is iron, and it is 0.014% of the sun. So very small amounts of those other elements. You don't have to worry about those, but you do need to know that the sun is hydrogen and helium. Okay, but what about all the other stars? You know, we're getting into the portion of the text about stars. So, while not always an exact copy, the makeup of the sun can be applied to all other stars in the galaxy. All stars in our galaxy are made up of the same materials. Now, obviously, the size is different. You know, not all stars are the same size as our sun. There are some that are much smaller, and then there are others that are massively bigger than our sun. Our sun is not the biggest. You know, it's not the smallest. But as far as like their makeup, they're all, with a few alterations here and there, in our galaxy, all of our stars are roughly made of the same portions. And once again, scientists can determine that by analyzing the light that comes from those stars. Even in various stages of their life cycles, stars are typically made up primarily of hydrogen and helium. So, that brings us to the end of this video. What I'm going to be expecting from you going forward, I will put up a small quiz here in a few days about the information I covered in this. But the stars is the section that we're on now. We're going to start talking about, we started with the sun, and then we're going to get into different types of stars. And one thing that I always enjoy talking about each year is talking about constellations. We will get into constellations, and we'll talk about specific constellations, their names, how they got their names, and we'll even get into a little bit of the mythology behind each of the constellations, because a lot of them have stories associated with them. So we will get into that, and it's going to be pretty interesting. I enjoy this section. So that's it for today. I hope you have a good day, and I hope to see you all soon. Bye.